Hi guys, so this is lesson 1 of chemical bonding and molecular geometry. Now up to page 26 should to a large degree be familiar due to the work we've done last year. So in this topic we will discuss chemical bonding, the types of chemical bonding we get, and we will also look at the molecular geometry of various molecules and how that is influenced by the distribution of electrons around the molecule. So to jump into the work, we first talk about our 3 types of chemical bonding that we get. Now last year we learned that we get the first one is covalent bonds, which represents the sharing of electrons. Then we get the ionic bond, which forms between non-metals and metals due to the transfer of electrons, where you've got positive and negatively charged ions attracting one another with the electrostatic force. And then we also looked at the metallic bond, which we get in metals. Now, these 3 types of bonds are referred to as intramolecular bonds. Now, intra means within, so it's the bond between atoms within molecules. Now, last year we learned about valence electrons. Now, what are the valence electrons and where do I find them? These are the electrons in the outermost energy level, and they have the highest energy. Now, why do they have the highest energy? Okay, if you think of it, electrons are charged negative, the protons in the nucleus is positive, so we can say the nuclear charge is positive. So there's an electrostatic force of attraction between these oppositely charged particles. However, due to the presence of these core or inner electrons, the force that the nucleus can exert on those outer electrons, our valence electrons, is weaker. The distance between the nucleus and those electrons is also bigger, and therefore they've got less attraction on those electrons. And because the attractive force is smaller, it means that those electrons now have more kinetic energy and they can move faster because they're not held back by that attractive force. So in this diagram, this is a representation of the electrons that we find in a phosphorus atom. Now I want to remind you, the first energy level over there, we've got 2 electrons. It only contains a 1s orbital and it can only take a maximum of 2 electrons. In the next energy level, the second energy level that we have over there we have a maximum of 8 electrons because there's an s orbital which can take 2, and then we've got 3 p orbitals which each can take 2 as well, so that gives us a maximum of 8. And then in our final energy level, our third energy level, we've got 5 electrons. Now I want to remind you of the following. Phosphorus is found in period 3. It has electrons up until energy level 3. It's found in group 15 of the periodic table. In old days, we had Roman numerals and we would say it's 5a. It has 5 valence electrons if it's in group 15, and it will obtain a charge of 3 minus if it becomes an ion. Why 3 minus? Because it needs 3 electrons in that final energy level, and it's easier energetically to gain those 3 electrons than losing 5. Okay, so we can also represent those electrons by using what we call an energy level diagram, or last year we spoke of a Aufbau diagram. I don't know why that screen keeps popping up. So an Aufbau diagram. Now, how do we represent the electrons in an Aufbau diagram? We use these half arrows to represent electrons, and remember they have to spin in opposite directions. And then we've got a 1s energy level, only 2 electrons. The 2s orbital, we've got 2 electrons. 2p, we've got 6 electrons. In total, in the second energy level, we have 8. Just a note on wording. So this is an energy level, and those are orbitals, and we sometimes call the orbitals also sub-energy levels. In the third energy level, we've got 2 electrons in the 2s orbital and then 1 electron in each of the p orbitals. A reminder here, it's very clear from this diagram that we first put 1 electron in each of the p orbitals before pairing them up. Okay, now this is a bit tedious writing these formulae like that, and that's why we've developed a shorthand, which we call an electron configuration. Now, electron configuration, also sometimes called the SP notation, where we have a shorthand for this Aufbau diagram. So in the 1s orbital, we've got 2 electrons, so we represent it with a superscript. In the 2s orbital, we've got 2 electrons. In the 2p orbital, we've got 6, and then we've got 2 electrons in the 3s orbital and 3 electrons in the 3p orbital. Okay, now remember here it says the number of valence electrons is equal to the group number. Remember, that's the Roman numerals, because today we talk about phosphorus's group as group 15, but it has 15 minus 10 electrons if it's in the groups 13 to 18. So 15 minus 10 would tell us it's 5. So just take note of that depending on the type of periodic table you use. So guys, what you now have to complete is exercise 1, and I'll be with you now to see if you managed that.